Hey guys, let us take a look of my latest publication regarding to the research in wine informatics. So the title of the paper is going to be using the full power of the computational wine wheel to understand 21st century Bordeaux wines from the reviews. There are three important keywords in the title. First of course, is the one I bolded. We want not only using the dictionary match, but also using the category as well as subcategory to include more information that we can retrieve from the wine reviews. And of course, the data set that we're going to use in this paper is going to focus on the 21st century Bordeaux wines. So here's the outline that we want to use for this presentation. Starting with the introduction, since many of you guys already have the experiences in wine informatics, as well as many data mining algorithms and data science experiences, the presentation here is kind of a extracted version compared with what we usually will do in the conference for the paper presentation. So the outline that we will start is looking into introduction, and then we will look into the data set. So how are we going to use the full power of the computational wine wheel to get additional attributes? It's going to be discussed in the data set subsection. Then we will look into the methods. There are major two methods that we implement in this research. One is naive Bayes, but more importantly, how would you do naive Bayes in a data set that has part of continuous value, part of binary value, and of course SVM. And finally, we will look into the results. So let's start with the introduction. In the previous research, we generated two Bordeaux data sets. The first one is the all Bordeaux data set that contains about 14,000 wines, and that covers all of the wines available in Wine Spectator from the year 2000 until 2016. A subset of that old Bordeaux dataset, which are the wines included in the classification, what we call the Bordeaux Wine Official Classification in 1855. So these are a set of elite Bordeaux. So all of this dataset contains 985 binary attributes, and you already see the data set, what the data set looks like, and many of you probably also tested or do experiment on this data set. So you should be very familiar with data set. The important keywords over here is the binary attribute. So you know that for every wine, except for the wine, name of the wine, price, several attributes that are describing the wine, the real attributes that we use are those binary attributes. So if the wine has apple as well as good finish, they will have those two attributes under the value of 1 to indicating they appear for those attributes. So those are binary attributes. So in this paper, we want to use the full power of the computational wine wheel. If you recall, the computational wine wheel actually have 4 columns. It has category, subcategory, exact words, and normalized terms. And therefore, previously we only used the third and the fourth column. We never used the information stored inside of the first column, which is category, as well as the second column, which is subcategory. So in this case, there are 14 categories in the computational wine wheel, and there are 34 categories in the subcategory. And therefore, but if we use those information, we can gain 14 new attributes from the category and 34 new attributes from the subcategory. And therefore, we want to see, since we can get new informations about the wine and we can describe the wine with more information, is that going to do any good to our research? More importantly, can the classification model built on these new information can gain more accuracies, which means they can understand about the wine more. And therefore, the goal of these papers is to incorporate the full power of the computational wine wheel to gain more insights in those 21st century Bordeaux wines. And not to mention, if that is the case, we can actually open up the new door about the wine informatics research, because all of the previous researches use only 985 binary data set, and now we have potentially 48 new continuous values that can help us describe the wine. We can know wine more, or computer can know more about the wine that we want to do the research on. And therefore, this is the whole ideas about this research. So in the case of the introduction, of course, I attached the paper in the blackboard, so you should be able to read, and you need to read the whole paper basically. So if you looked into the very first paragraph, which is something I want you guys to do for your own research as well, is that read the paper, you will understand even in the introduction there are 5 paragraphs, and each paragraph has its focus. The first paragraph of the paper is going to talk about data and data science. This paper I plan to submit into the journal that is not computer science journal. I'm going to submit a journal into what we call the beverage journal. So many people reading this may not be familiar with computer, may not familiar with the data as well as the data science. So I want to start a brief introduction to bring people into the field. And that's why we start with talking about data as well as the data science, and then use this to go into the domain knowledge, which we are talking about for all of the data science applications. You need to have a domain knowledge to walk into, so that you can collect the data in that domain knowledge. So that in the second paragraph, we talk about wine, and more specifically wine reviews, which is going to be the data that we want to use. And so that once we combine the data science with wine and wine reviews, we can make it to talk about the wine informatics, which related to our previous work. And once we have understand what is wine informatics, now let us take a look of the specific data or specific research area that we want to look into, which is Bordeaux. So we talk about what is Bordeaux, how do we collect the Bordeaux data set, and at that time, we have prepared everything, and we can go into the goal of the paper to briefly discuss about what is this paper about. So you can see that when I'm writing the paper, I have subcategories of every single paragraph that I want to write. And therefore, for the assignments that I want you guys to do, is that I want you to write your first paragraph, which is the introduction about your research. And I also want you to use the same structure. So I want you to write the outlines like this slide. So what you need to submit are 2 things. For one is the outline like this slide, plus the full complete introduction of your research. Every team need to prepare 1 paper paragraph. So that is what I want you guys to do as the assignment of this class. Then let's take a look at the data set. Of course, you may be interested, what is the data set really looks like? So the data or the wine review is collected from the wine spectator with 100-point scale. And of course, the scale has their own meanings. In this research, we try to focus on the wines that comes from 90 to 90, 95 to 100, and 90 to 95. 94. So obviously there is minor mistakes over here. We want to correct that one, and so let's do that. So you can see that in this research, we try to make it as a binary classification. So for the wine that are 90 plus are considered as positive group. The wine that's between 80 to 89 are considered as negative group. And of course, there are some wines that are not as good. It's basically not included in our scope. And therefore, you can see that if we look at example of the wine reviews and more specific about the Bordeaux wines, you can see this giving the name of the wine, talking about what's the vintage, what's the score, and how much does it cost over there. On top of that, try to talk about what is the wine review, what is the wine drinks like. And of course, this is in human language format, and therefore we developed the computational wine wheel to pick up the important keywords, not only the flavor words, but also the non-flavor, including like a body, finish, those kind of things, as well as some adjective, for example, phenomena here. And so those are the works has been done in the computational wine wheel. So we use the process the review through the computational wine wheel, which works as a dictionary to one-hot encoding and convert the words into the vectors. So for example, for wine with fresh apple as well as crushed cherry, if we map into our computational wine wheel, this wine will have one attribute that's considered as apple, because fresh apple will be normalized into apple, as well as cherry, because cherry is the normalized word for fresh, for crushed cherry. And therefore, this is what we have been done for the original data set. In this research, on top of those attributes, we are actually also using the category as subcategory, and we try to count how many times that the attributes in the category appears. So you can see that in this research, not only apple and cherry attributes will be one. The new data will count tree fruit twice, because both apple and cherry are considered as tree fruit, as well as fruity twice, since both apple and cherry are under tree fruit as the subcategory and fruity as the category. So you can see that now the data set has more information. It has fruity with count of 2, tree fruit with count of 2 as the subcategory, and then it has a value of 1 for apple and a value of 1 for cherry. And therefore, you can see that this data set is kind of a mixed data set. You have some continuous value, you also have some binary values. So you can see that this is the summary of the computational wine wheel. You have the categories over here, which I believe is 14 different categories. Each one of them has some subcategories. So fruit is the biggest category with the highest amount of subcategories. And each one of them has the mapping specific name. So we use the specific name, try to map into the reviews, and then normalize the value, provide a 1 for the normalized value as positive. And at the same time, we now try to count how many times does the specific name has been mapped in the subcategory as well as the category. Therefore, you can see this is like the whole process. The review will be processed through our third column, try to map some of the attributes are 1, and not only that, in our previous research, we stopped at this stage. Now we want to go further. We looked into the subcategory. So what is the vanilla being considered as the subcategory of? And then we try to count citrus, berry, fruit, finish, nutty, oxidized, those kind of things. How many times does this wine have those attributes? So we have some continuous value for subcategory as well as some continuous value for the category. In the end, we try to normalize the value by maximum and minimum sum of the column of the attribute. So in other words, after all 14,000 wine had been processed, for the column of fruity, we will use normalize, try to normalize all the values in between 0 and 1, so that we can get a value in between 0 and 1. And therefore, you will have some 0 to 1 values in the category, 0 to 1 values to subcategory, and binary values in the attributes of those 985 attributes. So that is how we generate our data set. And next thing is we try to see how do we do naive Bayes as well as SVM. Starting with naive Bayes, you should be familiar with this already. We use the probabilities to look into precondition as well as the postcondition, and therefore what we try to do is using that concept to do the naive Bayes classifier. We try to see every single attribute's probability contribute to the class, and then we can generate a probability for positive class and a probability for the negative class. The only question now is, in our previous class as well as the discussion, we all look into the binary data set. Now some of those values are binary, some of those are continuous. How can we do that? It's actually not that hard. There are two main naive Bayes classifiers based on the type of the attributes. For the naive Bayes classifier for binary attributes, which is the one that you have learned already, that's what we call Bernoulli naive Bayes classifier. So what we do is that we simply using the number of samples have attribute X and belong to the class of Y divided by the number of samples reviewed and belong to the class of Y. So that is the binary way of doing that. For the other one, which is Gaussian naive Bayes classifier for continuous attributes, what we have done is that a little bit more calculation, obviously. We need to use the sample standard deviation put into the consideration and using the exponential of the values that we have minus the average value divided by 2 times of standard deviation square. So that is how we will be able to get the probabilities for the continuous values. So now you have the question that for the first several attributes, they are continuous value. And for the rest of 985 attributes, they are binary values. So how do we do a mixed version of them too? The answer is pretty simple. We basically try to get a probability for the continuous values by using Gaussian naive Bayes classifier. And we can also get a probability for the binary data sets through the Bernoulli naive Bayes classifier. So we have two values now. Since both of them are probabilities, we multiply those two values for the positive case, and we do the same thing for the negative case, and which one is higher is the one that we are going to make the prediction of. So that is how we do naive Bayes classifier, like using two sets of values. For SVM, I don't want to spend too much time on that one. SVM is basically are able to handle that when SVM is looking into that original data set, although it's 0 and 1 binary data set. They try to draw the hyperplanes between the two, and now by adding some continuous values, SVM can still process those, and therefore there's not much change in the SVM, since what they try to do is try to find the maximum margin of the data set. And therefore, the same thing that we use for the evaluation metrics. We try to calculate the accuracy, recall precision, as well as the F-score using the 5-fold cross-validation. So that's how we evaluate our results. And therefore, it is time for us to see if the results are really better. The answer is yes, of course. Before we look into the results, I want to talk about how do we do the experiments. You know that we have a set of attributes coming from the category. We have a set of attributes coming from subcategory. We have a set of attributes coming from the fourth column, which are the normalized attributes. And therefore, before we do anything crazy, we simply try to see that what are the results if we only using 14 category attributes that coming from the category, as well as what happens if we only use those 34 subcategory. And what happens if we use 985 normalized attribute, which is the experiment results that we did or we presented in the previous research. So we can have some simple comparisons. Of course, if we only compare these three, the one that we did before must perform best because we know it actually doing pretty well, and compared with the number of attributes, more attributes usually provides more information. That's a hypothesis and what we try to see if that's true in this experiment. And then the fourth data set that we try to do is using all of those, and therefore this data set 4 is going to take the longest amount of time to do the training, and it is of course the biggest data set that we have. Then we try to see some combinations. So if we only put category as well as subcategory together, how does that perform? If we combine subcategory with normalized attribute, how does it do? And if we try to combine category and normalized attributes, how did they perform? So we have all 7 different kind of data set. Basically, the number of attributes are different from each other, and we try to see how do they perform. So now let's take a look at the results. Of course, if you still recall, the data set number 3 is the one that we were using. So that's our baseline to do the comparison. In this table, this is the result that we use naive Bayes on all Bordeaux data set. So for all Bordeaux data set, we tried 2 different algorithms. One is naive Bayes, the other one is SVM. In naive Bayes, you can see that for data set 1 and 2, which only use category as well as subcategory, they are not performing good at all. It's not bad, to be honest with you. It has about 75% for each one of them by using only a small number of attributes. It's pretty outstanding, actually. But compared with what we already have, it's not improving. So now let's take a look of the dataset 4, which is the one that use all of the attributes. Surprisingly, it's not as good as the previous one. So you can see the accuracy is actually dropped, precision increased a little bit, recall is actually not performing well, app score is not as good as the previous one. So the one that use all of the attributes is actually not doing very well in this particular setup. Then you can see that dataset 5 using category and subcategory is not performing well by judging into the app score. And of course, number 6 is improved using subcategory as well as the normalized term. But if you look into this one, this is actually doing better than the comparison. The dataset 7 is the one that uses the category plus 985 attributes, normalized attributes. The accuracy increased, precision also increased, recall dropped a little bit, but F-score, which is like the consideration of the previous 2 things, is actually doing better. So obviously, in this setup, all data set using naive Bayes classifier, we are actually can perform better with using the attributes coming from the category as well as the normalized term. If we look into SVM applied on the same data set, you can see that the baseline is pretty solid already, and the dataset 4 as well as dataset 6 is actually performed slightly better, 0.03% in accuracy. The results are very similar to one another. They haven't changed too much by using SVM. One important thing you need to understand is that SVM originally already achieved about 87%, which is like the top of the results already compared with the previous one. So let's take a look of the previous one. Previous one using naive Bayes is about 85%, so it's about 1 to 2% lower than SVM. However, after our improvements, this result is actually better than SVM. So in other words, additional information is actually not that helpful in SVM for SVM in all Bordeaux dataset. So now let's take a look of the elite one. One very different about the elite wine is that they now have more 90 points wines to 90 minus wines, unlike regular wine distributions. So let's see what's going to happen over here. So if we look into 1855 Bordeaux wines using naive Bayes classifier, you can see that the baseline is here, and our dataset 4, which use all of the attributes, actually perform very well. Especially the recall is going to be as high as 94% over here. So in this case, and for naive Bayes, using all of the attributes seems better in this case. And of course, dataset 7 is also doing better than the original one. And therefore, we can see that for this dataset, category as well as subcategory do provide additional information. Similar things for the SVM, you can see that the SVM is actually improved a lot by using all of the attributes. Now it goes up to 86%, which increased about 5% in accuracy and as well as like 4% in the F-score. And therefore, we can see that additional attributes do provide valuable inputs to the model. So now we see that dataset 4, which use all the attributes, versus dataset 7 that use category plus normalized attributes. We want to discuss a little bit which one is better. And of course, by looking into the figures, you can see in this case, if in using all Bordeaux dataset, the dataset 7 is actually better than the dataset 4 because you can see that for dataset 4, the blue ones, that's the one that using naive Bayes, are actually not performing well in most of those. And while we have looked into the dataset, understanding that because the dataset is kind of imbalanced toward the 90 minus 1, and recall is the one that try to capture how well do you do for the 90 plus 1, and therefore the result showed in here is less ideal. So that is what we have find out in the all Bordeaux dataset. Dataset 7 is actually perform better than dataset 4, which means that excluding subcategory is actually better in this case. For the 1855 Bordeaux dataset, now we have more positive ones. So you can see that the recall coming from the all attributes are actually better. So dataset 4 outperforms dataset 7 over there. So that's some findings that we have looked into while we try to do more analysis in the results here. So conclusion. For the all Bordeaux dataset with the additional attribute, naive Bayes classifier algorithms are able to outperform the existing researches by increasing 2.15% accuracy, 8.72 precision, and 1.48 F-score. For 1855, when SVM is applied, it actually can increase about 5% of the accuracy, 2.85 precision, 56% recall, and 4% of the F-score. So that this is the findings that we have found. And of course, this finding has the strong impact to all wine informatics that we have do in the previous work, including evaluating the wine reviewers, weather predictions, terroir for a specific region analysis, all kind of things. Then these may be useful to provide important insights or useful informations for winemakers, consumers, and distributors. So this is what I have prepared for the new papers that I've wrote. And of course, I want you guys to take a close look of the paper, try to understand the structure of the paper, and so that you can write your own paper for the next month.